afternoon, good evening, everywhere you're joining from. My name is Ana Capuano, and I'm a professor of neurology and public health at the University of Chicago and a visiting scholar at Harvard T.H. Chan School of Public Health. It is my pleasure to welcome you to the inaugural webinar of the ARISE 2025. This is an initiative of the ASA Statistics and Data Science in Aging Interest Group that I serve as educational chair. The RISE stands for Aging Research Innovations in Statistical Exploration and was developed to spotlight the exceptional work by early career scientists pushing the boundary of research in the intersection of aging, data science, and statistical methodology. Today, we are thrilled to open the series with 3 outstanding presentations. So we will begin with Owen Lee, who is completing his PhD in statistics at Lancaster University in the UK, under the supervision of Professor Rebecca Kulik. Professor Kulik is a leading research in change point detection and time series analysis with strong focus on translating statistical innovations into real-world application. And this project is supported through a partnership with the digital health company HOSE. So Owen's work focuses on detecting early signs of health decline in older adults living independently by modeling routine behavior patterns. In his talk titled Modeling Routine Behavior Using Change Points, he will introduce novel methods to analyzing periodic data, treating time as circular rather than linear. These methods are already being implemented as the main algorithm of HOSE customer-facing product. So our second presenter is Molly Ehrig. She's a biostatistician at the Wake Forest University School of Medicine, where she collaborates with the departments of emergency medicine and neurosurgery, as well as the Claude Pepper Older American Independence Center. Her presentation titled Imputation and Missing Indicators of Handling Missing Longitudinal Data, and investigates whether the missing indicators method improve performance in predictive modeling using longitudinal electronic health record data. And her simulation study focused on modeling fall risk on older adults. Okay, and then, so this work was mentored by Dr. Jamie Spicer, and she's an associate professor of biostatistics and data science at Wake Forest. Dr. Spicer's expertise span machine learning methods for longitudinal data and real-world predictive modeling in clinical research, with emphasis on methods that can improve decision-making in learning health systems. So our final speaker today is Tian Yuan, assistant professor in the Department of Statistics at Colorado State University. Her research focuses on statistic methods for high-dimensional, messy and complex data challenges, particularly in genomics, epidemiology, and EHR-based studies. She develops robust, interpretable, and computationally efficient solutions using tools like the quantile regression, machine learning, and the Bayesian techniques. In her talk titled Join Quantile Regression with Latent Clustering for Age-Dependent Genetic Effect, Dr. Yuan will introduce us a novel statistical framework applied to the UK biobank data. Her work explores how type 2 diabetes associated genes influence lipid traits and body measurements in premenopausal women, revealing age-specific and pleiotropic genetic effects. So her work was mentored by Dr. Iway and Yulita Lonita Laza, both from Columbia University. So Dr. Wei has a lot of work in quantile regression and functional data analysis, while Dr. Yolita Laza has a lot of work in statistical genetics, particularly in methods for analyzing complex genomic data. So we are honored to feature this exciting work today, and deeply grateful to these talents, the talent or early career scholars and their mentors. Some are here to discuss with us at the end for helping us launch the ARISE. So welcome everybody. We will have Q&A and discussions at the end, so after the 3 presentations. So please write your questions on the Q&A area there in the bottom, so we can keep track of it, okay? And with that, let's begin with our first speaker, Owen Lee. Please take it away.
Okay. Okay, cool. Hi everyone. I'm very excited to be here. So thank you for inviting me to this series. Today I'm going to be talking about modeling routine behavior using change points, and specifically how that relates to kind of the aging research impact that we've done here at Lancaster. And also, yeah, my work is supervised by Professor Rebecca Killick, who's also in this call. So if you have any questions for them, feel free to send it to them as well. Okay, so onto the motivation. So later on in this presentation, I'll show some real data, especially with this project is partnered with a company called House, and so I'll show some real data from them. But for just the purposes of the motivation, I'll just show the simulated data. So we have about 7 to 8 days worth of data here, all kind of normally distributed. And so if you look at like a specific day, so for example, from midnight to midnight, you might see that the data is kind of a bit random, and it kind of changes quite a bit. Or you could say, it might fit some kind of trend. Okay, but if you look at it across the multiple days, you can see that despite some variation, the kind of the behavior of the data is repeated across those days, and this is the kind of the data that we want to be able to model and behave, and what we call periodic data, and is the kind of data that we want to be able to study. So given kind of the repeated nature of this data, how do we study it, and how do we analyze and model this type of data? So we use a method called kind of change point. So here's the kind of formal definition of it. Essentially, a change point is a position or a point in time within your data where you can observe a change. Okay, where what that change is kind of up to the application and up to the data. And so here are some traditional examples of these change points. So for the first plot, we have a change in mean. So the data is fairly stationary, fairly stable up until this kind of time point 100, and then at some point the data changes. The mean of this data changes. Okay, and so at this point we call this time point 100 a change point, and you can have multiple change points throughout your data set. You can also have a change in regression and a change in variance. Okay, and due to the generic kind of definition of what a change be, we don't specify what a change is. It can be kind of anything. Change points are widely applicable to kind of some real world problems. For example, you have applications of change points in kind of online monitoring, kind of in as well as kind of like climate change and environmental impacts, and as I'll show later on, in aging research as well, particularly in being able to model the changes in an individual's activity levels / their behaviors. Okay, so given we want to be able to model the change points, I'll just give a little background on what the traditional change point methods in the literature are like. So traditional change point methods in the literature treat time as linear. So you can imagine the data points are plotted linearly. So one data point happens after another, and the change points behave in that same way. So one change point happens after another, and as soon as one change point occurs, the past data is almost kind of forgotten, and we just move on to identifying where the next change point occurs. Okay. Now, as I said before, this has many applications. This worked really well in a lot of scenarios, for example, like climate change or even like finance. But for periodic data or routine behavior, this doesn't work so well, especially in the case where, because with the routing behavior, we have the data, the behavior of the data is repeated across time. We want to be able to extract that information, that repeated behavior, in order to kind of model our data properly. Okay, so this is the same data I showed before, but this time I've kind of overlaid the true parameters onto there. So the blue vertical lines at the bottom show the true change point locations. And then this is a simple change in mean example. So we have the 4 changes in means. If you look at any particular day within this data, you can see that there's 4 change points. And we want to be able to kind of capture all, and these 4 change points are repeated across all the different days. And so we want to be able to capture all this. Now, if you focus on any particular day, you'll see that there are around 3 or 4 points which could easily be seen as outliers. Okay, like say, for example, up here. And due to kind of 3 or 4 points isn't a lot of information, especially because it's so different to everything else. You could easily, if you're just focusing on that particular day and you're running an algorithm kind of linearly, these could easily be seen as outliers and kind of disregarded as a pattern. However, if you look across the different days, you can see that, despite the variation, these 3 or 4 points aren't outliers and are repeated behaviors. And so we want to be able to kind of pick this up. And so traditional change point methods, which treat time as linear, aren't able to do this. And therefore, instead of treating the time axis as linear, we treat the time axis as circular in order to model the periodic data. So what this means is, if you can imagine, for example, let's say routine behaviors, we assume that occurs within a 24-hour period. And so if you imagine a 24-hour clock, and as you move forward in linearly through time, you go round and round this clock, and at each time point, you'll be collecting kind of collecting your data at each of these time points. Okay, so let's say you start from midnight, you start collecting your data across the entire day, and once you get to the end of the day, or kind of the beginning of the next day, as you move forward onto the next day, you kind of go back round and round in this circle. And so at every single time point within your day, you'll collect multiple different data points from the different days of data that you have. Now, so this is what we mean by circular time, and this is really important, and it's because, so for example, in this plot, it's the exact same data as before, but instead of plotting it linearly and across all the different days, I plotted it, what we say, circularly, and so at every single time point, you'll have different data points from the different days, and this means we can kind of use kind of traditional change point methods where we allow the behavior within this day to be random and to kind of change throughout the day, but we also pull the different evidence from the multiple different periods. Okay, so before we had about 7, 8 days worth of data, and so at each time point we have 7, 8 different data points, and that short segment of data before, where we had just 3 or 4 data points that could easily be seen as outliers, here you can see that there's a lot more information there, and you can see that these aren't outliers, but in fact it is an actual pattern occurring throughout your data, and so we are able to efficiently model this. Okay, so kind of given the background and the structure of our data now, I'll now kind of describe the algorithm that or the method that we've developed in order to kind of model this. And so we call this segment neighborhood in circular time, or SNCirc. So traditionally, in change points, we want to find 2 unknown variables. First one is just the number of change points. So this is we denote this as M. And given our M change points, we also want to find the best location for these M change points. Yep. So let's start off with, let's say I'm going to fix the number of change points, M. So let's say, for example, let's say it's 4. So where I'm fixing, so I'm only looking at where the best 4 change points are, and I'm only going to search for where the best locations for these 4 change points are within my data, within my circular time data. So step 1, so the first step is just to decide how to model your data within a segment of data. So between your change points, how do you model that data? So for example, you could use a maximum likelihood estimation. So if your data is binary, you could use a Bernoulli likelihood. If it's normal, you can fit like a mean. Yeah, a mean model or a mean and variance model, or you can even use like a linear regression model as well. So it depends on the data. So you decide on how you want to model that data, and we say this is kind of the cost between two change points. Okay, step two. This is very specific to circular time. So we want to pick the end of the data, which I call K, or the beginning. And so if you can imagine kind of like a circle, or the start of your period, so let's say from like a 24-hour day, you want to be able to pick efficiently where the best start time for this day is. Now you could arbitrarily say, midnight to midnight. However, if you do that, we have to start our algorithm somewhere. So if we start it at midnight, this inadvertently puts a change point at the midnight location. Now, for some people that might work great. They might go to bed like, for example, they might go to bed at midnight, and so you might see a change in activity levels. However, that's not going to be the case for everyone. And so if you force a change point at that location, that means all other change points will be suboptimal, and you won't get the correct answer. And so to overcome this, we look at every single starting position. But let's say for the beginning of this algorithm, let's pick the end of the data. Let's say K, let's say midnight, and then later on we'll be able to kind of vary this and optimize it. Okay, so given we picked how to model our data, and we picked the starting position, now we're going to step three, which is so given your M change point, let's say 4 change points that you want to place, we're going to find the best locations for those change points. And we do this, so EssensCirc does this does it in an efficient way, and I won't go into too much details, but it uses like a dynamic programming method. But essentially, it considers all the combinations of those 4 change points that you want to place within your data. It calculates the cost of it, so you can see within the summation here. So it kind of sums up all those different metrics together to give an overall number, an overall metric, or a cost for how well those 4 change points fit the data. Okay. Now, given that cost, you can then change the combination. So change the locations of where you want to find those other change points. And then if you check for all possible combinations, then you can then minimize across all the different costs to get the optimal combination of change points and or the optimal locations of those 4 change points given your starting position. And that's what I denote here as our CM K plus 1 to K. Okay, so that was obviously to find the best locations of those like M change points, of those 4 change points, given your starting position. So as I said before, we want to then be able to repeat these steps, so repeat step 2 and 3, but with different starting positions, in order to consider all the different possible change point locations, all the different possible starting positions in your data. Okay, to find the best fit. So by repeating steps 2 and 3, you get all these different costs, and then given all these different costs, we can minimize across all of them to be able to find the best starting position and also the best M location of change points within the data. Okay. So given we've now able to find the best location of change points for a fixed M, to find the optimal number of change points for this M that is unknown, we repeat the above steps from 2 to 4 for a range of number of change points. So it goes from 0 to all the way up to a capital M. For example, M could be, let's say 24. So you have like 24 hours in a day, 24 hours of data. So then you could check for all possible change points there, and then you get to minimize across all of them to then find the optimal number of change points. Once you've minimized them across all of them, you find the optimal number of change points, and then from the earlier steps, you can then find the optimal location of those change points. Okay. And we do that kind of through this equation, and then we also have this penalty term here, this beta, which controls against kind of overfitting by placing too many change points in your algorithm there. Okay, so that's a generic kind of overview of how our algorithm works. Now on to kind of the application of this. So our project is partnered with a company called House, which is based in the UK. And essentially their aim is to prevent hospitalizations in the older generation through early intervention and through digital health. And so they do this by placing these discrete passive sensors around this individual's houses, and which kind of picks up kind of this proxy for activity. So the data that comes in is binary. And it could be, for example, if they've walked in the hallway or not, if they switched the TV on or not, and if a door's been opened or not. And so they measure this they have this activity data in the home, and the goal is to, if they can identify any irregular behavior, which deviates from their routine behavior. For example, if they start waking up a lot during the night, they want to be able to flag this up early, as that might indicate an early sign of health decline. Okay, so we want to be able to pick this up early before these problems become a lot more serious, and before before it results in hospitalization. Okay, so in order to be able to do that, we want to be able to model their routine behavior to get a good sense of what their usual routine is like. And so the data that comes in is binary, and we've binned it so then it's every 15 minutes. And so every 15 minutes, if any of the sensors have been triggered, then we get a 1, otherwise it's a 0. Okay, so this is some real data from House, and we call this person 1. I plotted it. I've done a summary plot of this. So the data is binary, but I plotted kind of the proportions across the different times, across the different days. So we have about 7 to 8 weeks worth of data here. Each of the gray lines, if you can see between the different ones, each of the gray lines represent a week's worth of data. And so they show the daily proportions for that week. And you can see, there's some variation there, but the black line shows the overall proportion, the overall average activity during any particular time during those 7 to 8 weeks. Okay, so you can see the different variations between the gray lines between the different weeks, but there is a general pattern occurring throughout it. So, for example, there's low activity detected during the night. And then during the morning, there's a quick increase, a big spike in activity, probably due to their morning routines. Some changes in activity during the day is a bit random. And then again, another spike in activity during the nighttime. Okay.
When we have 1 minute, okay? Let's try to wrap up.
Sounds good. Okay. And so, given these different activities in the day, we want to be able to model it. And so we run our SNCirc algorithm on this, and this is what we get. So the blue vertical lines are the estimated change points that we get. And the red lines, so in this case, because the data is binary, we just fit a Bernoulli likelihood onto this. And so it's essentially measuring a changing mean, but also estimating the probability of any of these sensors being detected. And so you can see that using this change point, using SNCirc, we're able to model this quite well. We can, it splits up the nighttime routine and then identifies the segment here in the kind of early morning routine. So because of the randomness there, it only decides to fit the optimal change point here, decides to fit 1 change point to account for the different randomness during the day. And then it also identifies the evening routine here. Okay. So this is the work I've done in my PhD for a couple of years ago, and I'm really happy to say that House is using this algorithm now, as well as an extension that we've done in their main algorithms, and it's having a direct impact into aging research and to kind of people's lives. And that's everything. So thank you for listening.
All right, thank you. Molly, please, let's jump into you.
Okay. Okay, can everyone see my screen and hear me okay? Okay, awesome. So hi, my name's Molly, and today I'll be talking about our simulation study to investigate the missing indicator method for handling missing longitudinal data. So the electronic health record has many analytic uses, including patient monitoring, clinical decision support, and quality improvement projects. However, because this data is not collected for research purposes, it's often incomplete, which means that there's missing data. So missing data can be considered ignorable when data is missing completely at random or is missing at random. And the assumption that electronic health record data is always missing at random may not be plausible, and previous research has shown that there may be a mixture of random and non-random missing mechanisms. So in data analysis, there are a few different ways that missing data can be handled. The most common is complete case analysis. So this is when all observations that are missing any analysis variables are removed from analysis. And this may result in an unbiased analysis if data is missing completely at random, but will result in biased results for missing at random or missing not at random. But no matter what the missing mechanism is, it results in a loss of statistical power because it removes observations. So imputation involves using observed data to estimate and fill in values that are missing through regression approaches. And we have regression imputation versus multiple imputation. And multiple imputation is regarded as the gold standard when data is missing at random, but there still may be biases when data is missing not at random. So that brings us to the missing indicator method. So this method adds a binary variable to the model that takes a value of 1 if the variable is missing and 0 if it's not missing. And this approach takes advantage of the information contained in missingness itself. So it's been introduced as a method when missingness is informative, or when the presence or absence of missingness adds prognostic information to a model. So recent research has raised concerns that the missing indicator method creates a negative feedback loop between clinical decision models and providers. So for example, this would be if a provider knows that taking versus not taking a measure is informative, then their decision to take the measurement may be impacted. However, other research has shown that the missing indicator method increases predictive performance when missingness is informative. And they also found that it didn't harm predictive performance when missingness was not informative, which is important because there's no way to test what the missing mechanism truly is. But this research was evaluated for cross-sectional data. So there's currently a gap in knowledge regarding the effectiveness of including missing indicators in longitudinal data modeling. And this is an important context to study the missing indicator method because the correlation within clusters may be leveraged to increase imputation accuracy and model performance, even when data is missing not at random. So the objective of our study was to assess the missing indicator method for longitudinal repeated measures data using a simulation study that mimics real-world EHR data. And our motivating example was EHR data that's used to study falls in older adults. So falls are the leading cause of fatal and non-fatal injuries among adults aged 65 and older, with 1 in 4 adults reporting falling each year. And two variables that we simulated related to falls are gait speed and single leg balance. So gait speed is a validated method for assessing mobility in older adults, and research has shown that slower gait speed is related to increased fall risk. And single leg balance is an assessment of balance and stability in older adults, and it's a common clinical tool for evaluating fall risk. Okay, so now I'm going to go through a summary of our approach, and then in the following slides, we'll get more in depth about these different steps. So first, I hope you can see my mouse. So first we simulated our data, so patient level and visit level variables, and we simulated our outcome. And we did this in 2 ways. So one where we included the missing indicators that we created in the model for simulating the outcome, and one where we did not. And then we induced missingness under 2 missing mechanisms, missing at random and missing not at random, at 2 different overall target missing percentages. And then you can see from here that we branch into the main things that we want to compare. So these different approaches are including missing indicators in imputation and modeling, not including missing indicators in imputation and modeling, and then complete case analysis. And this is a simulation study, so we did this 250 times, and then we aggregate our results and present a summary. So we simulated 250 patients with 5 visits per patient, and we simulated a mixture of patient level and visit level variables. And these include demographic, medical history, physical function, medication, and noise variables. So our outcome variable was binary, and it was whether a patient fell in the last year or not. And as I said earlier, we simulated this 2 ways, with and without missing indicators. And we simulated the variables to be related to each other. So for example, gait speed was simulated using a linear effects model that included age, BMI, diabetes, and sex as predictors. And then on the right here, you can see just an example. So this is from like one simulated data set. And you can see that in years that a fall occurred, gait speed and single leg balance are lower, and patients were more likely to be on medication. Okay, so we targeted two different overall missing percentages, 20% and 50%, and we induced missingness in four variables. So we did gait speed, single leg balance, pain medication, and depression medication. So to induce missingness under the missing not at random mechanism, the probability that these variables would be missing was dependent on the value of the variable itself. So for example, for gait speed and single leg balance, if the value was less than the 25th percentile, then the probability that the value would be set to missing was 70% for 50% overall target and then 30% for a 20% target. So this means that lower values of gait speed and single leg balance are more likely to be missing. And then similarly, if a patient was on medication, then their value was more likely to be missing. But to induce missingness under missing at random, the probability that the four variables are missing depended on the value of observed variables. So here we have age, BMI, diabetes, and urinary incontinence. And specifically, you can see in this plot, so the probability of being missing is dependent on these four variables. So this probability was higher for older patients, patients with a higher BMI, patients with diabetes, and patients with urinary incontinence. And then based off of that probability, we created these missing indicators. So one for each variable. And then if this indicator was 1, then we would set the value to missing. So at this point, we have created missingness and we have our indicator variables. So after doing this, the next step was imputation. So we used the mice package in R to impute, and we did regression imputation rather than multiple imputation because previous research has shown that regression imputation performs pretty similarly to multiple imputation when your objective is prediction rather than model interpretation. So the two-level structure of the data was taken into account by including patient as the cluster variable, and then we included all variables in the imputation model, including the outcome. And then as you saw in that flowchart, we did imputation in two different ways. So one way was with indicators and one way was without indicators. And the missing indicator for the variable itself wasn't included in the model because it would always take the value of 0, but the other 3 indicators were included. So we use 3 different performance metrics, 2 to evaluate imputation quality and 1 to evaluate model performance. So to assess imputation quality for binary variables, we use the proportion of falsely classified imputations, and this is defined as the number of incorrect binary imputed values divided by the total number of imputed values, where lower proportions would indicate better quality. And then to assess imputation quality for continuous variables, we use normalized root mean square error between the imputed values and the observed values, where again, lower is better. And then to assess model performance, we did area under the receiver operating curve, where a higher AUC would indicate better model performance. Okay, so now we're going to discuss results. So just to orient you to the plot, so first we have percent falsely classified, and this is on the y-axis. So remember, lower is better. And then results are broken up by missing mechanism. So on the top, we have missing at random. On the bottom, we have missing not at random. And by whether indicators were included in the model that was used to simulate the outcome. So that's why there's 4 different plots. And then within each plot, we have both variables, and then we're comparing indicator versus no indicator for our 2 different missing percentages. So we have 20% in this orange and 50% in the blue. And then the dots are the averages across all of the simulations, with the top of the bar being the 97.5th percentile and then the bottom being the 2.5th percentile. So for missing at random, you can see that the percent of falsely classified proportions was about 46 to 47% for both variables, regardless of whether indicators were used to simulate the outcome, and also really regardless of whether indicators were included in imputation and modeling. And you can also see there's pretty low difference between 20 and 50%. But for missing not at random, the percent falsely classified was about 52 to 53%. For 20% missing data and 61 to 63% for 50% missing data for both variables. And whether indicators were included in the outcome simulation didn't really have an impact, and also there was little impact between indicator versus no indicator in imputation and modeling. So overall, though, we can see that for missing not at random, the percent falsely classified was worse than missing at random. Okay, so now we have the exact same plot, but with root mean square error on the y-axis. So again, here lower is better. So in general, the error of single leg balance was a little bit lower than gait speed, but not by very much. And for both variables, error was higher at 50%. As you can see here, the blue had higher averages. It was also higher at missing not at random when you compare to missing at random. But whether or not indicators were included in outcome simulation didn't really affect error. And then when we look at indicator versus no indicator in imputation and modeling, for gait speed, error was slightly larger when indicators were included in the imputation model. So like you can see 1.06 to 1.01, like 1. These are pretty similar. But again, it's like not very much, and there was no clear pattern for single leg balance. Okay, so now we'll look at model performance. So AUC is on the y-axis, and here higher is better and indicates a better model performance. But all of the AUCs were around 0.75, and it didn't seem like the amount of missing data or the missing mechanism had a large impact on AUC. And you can see that complete case analysis had the largest spread of AUC values. Whereas there was not really a difference in the spread between indicator versus no indicator, and in general, like all of the intervals are overlapping with each other. So ultimately, from this study, we conclude that the missing indicator method did not improve imputation quality or model performance for longitudinal data, even when data was missing not at random, but their inclusion was not harmful either. And while AUC for complete case analysis was similar to AUC after imputation, we would not recommend complete case analysis because the increased variability can result in a loss of power. And also here, we weren't looking at model coefficients or interpreting anything. And when data is missing at random or missing not at random, we know that that can result in biased estimates. So there are multiple strengths of our study due to the simulation framework. So a major strength is the ability to define and control the missing mechanism, as there's no empirical test to see whether your data is missing at random versus missing not at random. And usually you would have to make an assumption, but here we didn't have to make one. Additionally, we were able to evaluate imputation quality because we know the true value of the variables. But there were also limitations. So the first is the quality of the binary imputations. We were surprised that imputation performed only slightly better than random guessing, which may have impacted how beneficial the missing indicators were in modeling. So we hypothesized that some of this error could be attributed to rounding to force the imputed values to be binary. And future work could investigate the accuracy of imputation methods for multi-level data. And other limitations were that we did not investigate time-dependent covariates, and we had to make assumptions about how the variables were all related to each other, which are most likely oversimplified. And future work could evaluate how the addition of more visits, missed visits, dropout, and other missing data patterns common in EHR could impact results. And we could also look at an informativeness parameter to see how the missing indicator works as missing data becomes more informative, or we could evaluate the missing indicator method with longitudinal data in other settings, like high-dimensional data. So I want to thank my study team, especially my mentor, Dr. Jamie Spicer, for mentoring me through this project and telling me about this opportunity. And if you scan the QR code, this will take you to our paper. So thank you so much.
Thank you. Good timing. All right, Dr. Wan?
Here, let me share my screen. Can you see that?
Yep.
Oops.
Oops.
Sorry, what did I do? I was trying to go to the full screen. Okay, is it good now?
Yeah, it's perfect.
Okay, sounds good. Thank you. First, thank Anna for the introduction, and I'm very glad to take this opportunity to share my recent research with you. This is a joint work with Yingwei from Biostat department at Columbia University, and also Yangyuan Ma from Statistics department at Penn State University. I am currently an assistant professor at the Stat department at Colorado University. So the topic is a joint quantile regression with latent clustering for age-dependent genetic effect and multiple traits. It reads very complicated, But let me walk you through this. So we develop a method to estimate the age-dependent dynamic progress of genetic effects, and we further explore how this effects links to multiple response, which is multiple traits here. Those are all related to the aging process. So first, let me start with some background. Aging is a multifaceted process. It's a lot of traits or phenotypes are associated with aging. People experience like the decrease in muscle strength, cognitions, and those like all related to the process of aging, and they are associated with genetic factor. So our main interest is how can we model this dynamic genetic effect process with respect to aging. There are two key features that really make us motivated and really get interested in this research. First is it's a temporal dynamic of genetic influence, and of course, for different people, that may also shows as different, slightly different process. And secondly, for genetic factors, it has a polyotropic nature, which means the single variant or a gene may not only associate it with one phenotype, it could simultaneously impact multiple traits together. So this makes our study more complicated because those are all intertwined together. We want to model a dynamic process, while those processes may not related to just one trait, it may relate to multiple traits together. So how can we put everything together into one unified framework? In general, we have data that's collected at different age for the same individual. It could be for the same individual, or it could come from different individuals. And also we have genotyped information so that we observe the ACGT base pair of the genetic profile for everyone. And we have multiple traits correlated together with this aging process observed here. So we like to model how this genetic effect associated with multiple response and how it's progress or evolve along the time. And most existing literatures will just investigate how a single variant influences one single trait. So just pick one dot here, analyze how the effect at a fixed time. So they don't consider the evolve of the timeline and also its simultaneous connection to multiple response here. And here I'm showing you a very basic preliminary toy example. Imagine now we have different traits. Here I listed 9 different traits. Some are lipid traits like high density lipoprotein, low density lipoprotein, triglycerides, and some are body measurement like waist, height, weight, BMI, and this one's glucose. Those phenotypes are correlated together. And if we just simply use linear regression, but because we want to estimate their time evolving effects, so we use a varying coefficient model with a linear regression, and what's shown on this plot is the estimated genetic effect function with respect to time, and each line corresponding to one trait. And those for genetic components, we're considering the polygenic risk score related to type 2 diabetes because those traits are all correlated together. So we want to see how those genetic components that contribute to type 2 diabetes may also have similar effects to other traits. So from this figure, we essentially saw 2 key messages. First, the overall genetic effect is very weak. If you look at the y-axis, it's very close to 0. And second, some of them can be clustered, like showing similar patterns, but some are standalone away from others. So this motivates us to, while estimating this genetic process, we want genetic evolving process. We also want to know, can we identify some latent cluster, some latent group that tells us how does those genetic effect play similar role in different traits? So here, just summarize what I just said. The genetic effect is weak and we need a large sample. UK Biobank will allow us to do this, but meanwhile, we want to identify the latent cluster. So we consider the varying coefficient linear and quantile model, and in the end, we choose the quantile model because of a lot of traits like BMI, they're highly skewed, they're highly heterogeneous. So the quantile model will give us a full span view of the distribution of the trait. And there are multiple studies showing that the quantile-based approach will enhance the power of detecting the heterogeneous effect and identify specific disease-associated genes, because those genes may not impact everyone. They may only affect a small group of the population. So we propose instead of just marginal time-varying models, very classical in statistics, we propose we can incorporate the underlying pleiotropy pattern as a latent cluster. So the reason we want to identify these latent groups is from two perspectives. Scientifically, it's meaningful because that helps us identify the genetic pleiotropy. It will uncover how a single genetic factor can influence multiple traits and revealing how those mechanisms are working together. And secondly, it enhances statistical power because after we have some grouping results, grouping labels, we essentially can pull the individuals as having the same effect together so that if enhance the statistical power, which will be very beneficial for identifying such weak genetic effect. So essentially, this work provides a way to simultaneously estimate the time-evolving, time-dependent genetic effect on multiple traits and identify the latent groups. So let me quickly introduce a model with some notations. First, we use I as the subject and K as different trait. For example, height, weight, BMI, those are all different traits. So for response, we have YIK. And we have some demographic covariates, including the intercept. Those could be like gender or race, ethnicity. And TIK would be observed age, and XIK here we don't consider a high-dimensional case. We consider one genetic variable like polygenic risk score, PRS. That's like a weighted sum of all the genetic components that related to this disease together as one variable. So this is our quantile model. For a fixed quantile level tau, we model this conditional quantile regression, quantile level of YIK as a function of XTC in this form. So let me explain, starting from the simplest term, the C transpose Kc. You see that there's a K associated with Kc. So we don't group the effect from covariates. Those covariates can have different effects for different traits, for different response, the case response. Where we have alpha T, alpha with this group membership L, and it's a function of observed time T. So this is a time-dependent function representing the genetic effect that change through time. And we have the L here means it belongs to the L latent group. So we will also have a gamma representing the group membership, saying that if for the K trait, if it belongs to the L latent group, then it will have this alpha of L, which is an unknown function that's changed over time. So the gamma, the alpha L, Kc, and also the total number of group M are all our parameter needs to be estimated. So our goal essentially is to estimate the function, genetic effect function evolving through time and gamma and Kc, and here we consider T between 0 and 1 for our theoretical property derivation purpose. So now the first challenge is this alpha, because we don't know gamma, we don't know alpha, we don't know Kc. And if it's an unknown function of t, how can we estimate it? So we take one step back. So now assume that we know the gamma. If we know the gamma, the only challenging would be we don't know the form of this alpha. Then a very natural idea is to use a B-spline to approximate it. It has been shown in the literature that we can use a B-spline to approximate this unknown function alpha. So all of that is under the condition, under the assumption that assume we know the group membership gamma k, so that we can write this unknown function as a product of a basis B transpose some unknown parameter theta. But essentially, after we can write it in this form, this approximation form, then we can just solve it as a regular quantile linear regression form. So this one can be solved by minimizing the following check function, the check loss in quantile regression. The reason here's a hat is because we do the B-spline approximation. Okay, so far we tackled the unknown alpha part, but we still don't know what is the gamma, the group membership, and we still need to estimate it. So essentially, we use the iterative algorithm. First, everything on this page define the initial value, the initial status. So for initial status, we just, for all k different traits, we just do marginal quantile regression with B-spline approximation. So there's no membership needs to be estimated. And then we use the k-means algorithm to pull those estimators together and to minimize the distance and obtain our initial estimator. Then given a specific m, we iteratively update the theta and c given the group membership gamma, and then we update gamma given the minimizer of the loss function. Finally, we propose an information criterion to choose the group number m. And this will be our final estimated quantile function with the theta hat, gamma hat, and c hat. So now, since due to a time limitation, I'll just quickly show you what theoretical property we have. Those are the regular conditions that we usually have, that people usually use when they use the B-spline approximation. And essentially, we guarantee that with a large sample, our group membership will be correct. And our choice of the total number of group will be correct. And our estimator has a consistency as well as the asymptotic normality. So those are all guaranteed. So now let's take a quick look at the real data example. We applied it in the UK Biobank data, and we focus on the group of overweight women aged between 40 to 70. That's the important physiological and metabolic change time during and after menopause. So there are total 21K subjects remained, and we're focusing on this tail overweight people with this distribution as the age histogram. So we pick again those 9 traits you've seen before. X is the polygenic risk score for type 2 diabetes. Those are all correlated together so that they may share some same genetic effect across different traits. And you can see they are all skewed. So that's essentially the heterogeneous of the data that also motivate us at the very beginning to using quantile regression. So if we just
1 minute, okay?
Sure. If we just do the marginal quantile regression, then you will see that those patterns change with the quantile level, and sometimes they may show some groupings, and sometimes they have the standalone group. But if using our method, you will see that they're actually grouped together at the median, and the glucose standalone starting from the median and also maintained at the upper quantile level, where the rest of us kind of goes towards 0, because this interval, if this interval band contains 0, so the genetic effect for the upper quantile is not very significant here. So I'll skip some more comparisons and go to the conclusion. We propose a joint quantile regression model. It simultaneously identifies the age-dependent genetic effect function and their underlying latent grouping, the pleiotropic patterns. And this algorithm is scalable for large-scale data set. It runs very fast, and we have the theoretical guarantees for the estimators and for the function itself. Yeah. Finally, I would like to thank again for my collaborators and for the UK Biobank projects and our grant support. Thank you.
Very good. Thank you, the three speakers. We are the very little time for discussion and questions. Next time we need to be a little quicker, but I'm going to extend a little bit. Who can stay is invited to stay. We have a question from one of the panelists. So, Dr. Kyoki, I will just ask you to go ahead and ask the question since you have open mic.
Yeah, so I've got a question for Molly. So when you were
Mhm.
considering generating the missingness, was the missingness across the explanatory variables done independently, or did you simulate it so that if one of the explanatory variables was missing, you're more likely to see the others?
Yeah, great question. So for missing not at random, it was based like off of the value of the variable itself. So like lower values, for example, of gate speed were more likely to be missing. And because of the way that we had simulated the data, like lower value of gate speed, you're more likely to have a lower value of single leg balance. So in that sense, there's some correlation, but we didn't like make that more explicit. And then for missing at random, there was one probability of being missing generated, like for each visit had its own probability, and then the missing indicators were all based on that one probability. So there you were more likely to be missing single leg balance, maybe if you were missing gate speed, but we did Bernoulli random variables, so there wasn't like complete correlation where you were always going to be missing all four or always going to have all four.
Okay, that's great. Thank you.
Very good. Yeah, I have a quick, I have questions for Owen and Dr. Wang. So we'll start with Owen. Like Owen, very interesting. I have some work there, as Charlie that posted on on the chat on change points, like on nonlinear. It's very interesting that you're looking at that circadian, right? Like how things work on the clock, and then they are connected at a certain point, right? If you think about things start over, right? You start over and over. So the question is, the method is very interesting, can be used in several different settings. Did you start to develop a tool for application like R package, and are you thinking about that in your dissertation?
Yeah, great question. So I've written, so the R package is written. The R code, it's really easy to implement the kind of the different methods in different settings, depending on your data. So with House, it was kind of Bernoulli data, but it was really easy to implement like normal data, and I think they wanted Poisson as well. So the R package is getting developed, and hopefully it'll be it can be used by everyone.
Yeah, and the code's available in the JIT or GitHub.
It will be, yes. So currently,
Will be.
I have a private repository with House just to check because it is the code for.
Okay.
But
Yeah.
when we develop the R package, it will be available for public. Yeah.
Very good, very interesting. And mostly, and you can look because there are 2 points, like you said, right? It is level and change, right? It looked to me that you look a lot like into the level, right? That was kind of the main focus. But one can also ascertain the slopes within, right? That's a natural.
Yeah, definitely.
Very good. The second question is for Dr. Wang. I was always fascinated by quantile models, like looking at loving things that are normal. And So I'm really glad that you work with that model in developing in genetics, and I can imagine that what you develop can be applied to very different settings than genetic. I wonder if you explore that and could tell a little bit about other applications within aging, you know, of the quintiles, if you thought about that, or
You mean the more general or the extension of
yeah,
this?
more general, because you're looking at several traits, you know, and there are different settings that you can have that, right?
Yeah, exactly. So currently we're using quantile regression, not only looking at the genetic level, but also genomic, like protein or gene expression. And we pull those data together and combine it with the EHR data and trying to find through this
Mhm.
doing the data integration, can we find or some more complex patterns through the quantile regression? Because for diseased people, they are only a very small portion of the population. So the difference must happen at the upper quantile or lower quantile. It's definitely not in the middle, especially for those rare disease. We use quantile regression, really find some interesting results for the rare disease. But those because they have only small portion of people are affected. So quantile regression would be a more powerful tool and can definitely help find the very specific evidence that usually the mean model, the linear model would miss.
Right. Now, you could also work your way around with ordinal models, right? Did you try that, compare to that?
Yeah, we tried it and we found that for a quantile model, it often can find a more heterogeneous signals, which means those might be like some environment gene environment interaction or gene interaction or so-called like epistasis, and those could be missed by linear regression but can be caught by quantile regression.
Right. So probably ordinal would be somewhere in between, you think, in terms of power, or since in with the idea that with ordinal you don't have the assumption of normality, right? Then
Right.
you can actually use anything, right? With some caveats to the extreme boundaries, but I'm just wondering if you play with that, as to how would it would compare if you use something like, like ordinal, like proportional odds or something like that, that it has you know what I'm saying? Yeah.
Right, that's a very, very interesting direction. Now we haven't explored those like ordinal data and related approach yet because we're currently focusing on the quantitative traits so far, because quantile regressions are mainly dealing with the continuous response so that you can define the quantile of it. For the
Mhm.
ordinal, it might be a little bit harder, but there are a lot of interesting problems there waiting for it being explored.
Yeah. Yeah, yeah, I think for binding, right? Putting
Right.
in beings, and then you could, yeah, very, very good work, everybody. Let me see if we have any final. I don't think we have any final questions, but amazing presentations. Thank you so much. We will have this recording, and you're going to be looked by others, and I'm very excited to wrap up this first webinar. Thank you so much for contributing.
Thank you for organizing this.
Thank you so much.
Yeah, thank you for organizing. Thanks, everyone.
Thank you. Bye.